Today I want to let you in on a really neat trick that I learned from a very famous mathematician. How to subtract infinity from infinity to get exactly pi. So for that I'll return to this blackboard here that I found in The Simpsons and I discussed in this video up there. And particularly that infinite series down there at the bottom. Okay, so it's 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 all the way to infinity. An infinite series with sum log 2. So that's about 0.69. What I want to do here is something that somebody discovered about 150 years ago. So just see what I do. It's a bit of a paradox. So what I do is I take a bit more of this, and I really need the whole board. So we'll take out every fourth term, and then what's left over has odd denominator and even denominator terms, so let's separate those out too. Now we're going to work our way in from the left, take those two guys and put them down there, take those two guys, put them down in the gap, take those two guys and put them down in the next gap, and you keep on going like this. And obviously when you do this, you use up all the terms that were there in the beginning and just rearrange them here and re-bracket them a little bit. Now we're going to work our way through the brackets. So first one here, 1 minus 1/2 is 1/2. 1/3 minus 1/6 is 1/6. And so on, right? So you can see how this works. It's a nice pattern here. That's what happens. So we've just rearranged the terms and we re-bracketed them a little bit. And that should not change anything about the sum of this thing, right? So if you compare what we've got now to what we started with, well, the bit that we started with is what? Log 2. But now we can compare term by term. So 1/2 of 1 is 1/2. 1/2 of 1/2 is 1/4. And 1/2 of 1/3 is 1/6. And so on. And so what you see is that term by term, the bit at the bottom here is always 1/2 of the bit at the top. So what that means is it should really be equal to 1/2 log 2. Now, if you put all this stuff together, you get log 2 is equal to 1/2 log 2, which really amounts to the same thing as saying that 1 is equal to 2. Oh. And whenever you come across something like this, you start worrying. So there's really two different options here. The first one is maths is broken, or we made a mistake. What do you think is more likely here? Well, yes, we made a mistake. So where's the mistake? So let's have a close look. So there was 3 different identities, so here, here, and there. So 2 of these are correct, and 1 of these is not correct. So the first bit, well, I already said this, and just believe me, this is equal to log 2. Then the bottom bit is also correct. In fact, that bracketing here, and I just say this now, you can put in brackets any way you want. It's not going to change anything about this sum here. It's always going to add up to 1/2 log 2. It's correct. So what's really messing things up is that we are rearranging the terms. So we're changing the order of the terms, and that really creates an infinite series with a different sum than the one before. So basically, when we're dealing with these infinite series, unlike with the finite ones, order matters. Rearranging the terms may change the sum. Okay, well, some people are getting really worried. Oh no, maths is broken anyway. No, it's not broken. We just have to get used to this. And got to be careful about this whole stuff. So we just saw that we can rearrange this series into another series with a different sum. And actually there's a famous mathematician, Bernhard Riemann, who came up with a theorem, the Riemann rearrangement theorem, which says that, well, in this case of this particular series, you can rearrange this thing into series that add up to anything you want. For example, pi, and I'm going to show you how that is done, how he makes up these different sums. Now, you've probably heard this name. The Riemann hypothesis is at the moment the most sought after thing that you can prove in mathematics. So eternal fame awaits if you can do this. And that's all about the Riemann zeta function. And there's also the Riemann integral, which you use all the time, and lots of Riemann named bits in mathematics. So this guy is a mathematical superhero. Usually, when it comes to these things that are named after him, quite difficult to explain properly, but that Riemann rearrangement theorem I can do like this with my animation magic. So let's just do it. But before we do it, I really have to remind you of what it actually means for one of those series to add up to a certain number. So, okay, so what we do is we translate this series into a sequence of numbers, the partial sums, the sequence of partial sums. So the first partial sum is just the first term, which is 1. The second partial sum is just those two guys added up. That's 0.5 in this case. Then third partial sum, fourth partial sum. And so you get this sequence of numbers here. And in the case of this series, the sequence of numbers converges to a certain number, which is log 2. And then we say that this series has sum that number, log 2 in this case. So that's the definition of a sum of an infinite series. So this is an example of a convergent series, a series that actually has a sum, which is a finite number. Now there's also lots of series that don't converge, and they're called divergent. So for example, if you replace all the minuses in here by pluses, I already showed in that other video there, that this adds up to plus infinity. But there's other types of divergence. So for example, if we take this guy there, it's 1 minus 1 plus 1 minus 1. The partial sums here are 1, 0, 1, 0, 1, 0. They don't settle down to anything. Not finite, not infinite. That's also divergent. So different sorts of divergent. To explain what's going on here, let's have a look at the positive terms and the negative terms separately. So if you just add up all the positive terms, you'll actually find you get infinity. And if you actually add up the negative terms, you get minus infinity. And actually, if you've watched the other video, you should be able to prove that yourself and maybe do it in the comments. So what we're really doing here is we're subtracting infinity from infinity in a controlled manner. What Riemann's rearrangement theorem now says is that if you've got a convergent series whose positive terms add up to infinity and whose negative terms add up to minus infinity, then you can rearrange this series into series that have any sum you want. So let me demonstrate this now for pi with this particular series. Okay, so we want pi. That's positive. So we're going to start with some positive terms. So the first term of my new series is going to be 1. So the first partial sum is also going to be 1. So partial sums I put up there. Well, that's not enough, so we add a few more of those positive terms. Let's get close to pi. Now, you actually have to add quite a few of them to get close to pi. We're still just under here. So let's add one more. Let it get us just over. This string of terms we choose as the beginning bit of our new series. So we're just over. Now we're going to use some negative terms to get just under. Okay, so we use actually the minus 1/2 is good enough. So that gets us under 2.6 and so on. All right, now let's go over again. So for that, we'll just use some positive terms. We actually need quite a few again, but we can be absolutely sure that we can get over because at any stage of this process, the positive terms that are left over will add up to infinity and the negative terms that are left over will add up to infinity. So I can always be sure that no matter how far I'm under or how far I'm over, I can always take enough terms to get under or over. All right, now we can just keep on going like this. So then a negative term to get us under again, then a positive terms again to get us over, and we go flip back and forth, and eventually we get to pi. And we can also be sure that we get to pi because the terms themselves, they get smaller and smaller in magnitude. So that means that as I overshoot and undershoot, I get closer and closer to pi. And actually, I can rearrange this initial series in infinitely many ways, different ways, to get me pi. I can also rearrange it to get me an infinite sum, all sorts of other things. So maybe you also want to do this in the comments, figure out the details there. Now for other series, you can actually have the situation where nothing changes no matter what you do. So there's lots of convergent series where the positive terms add up to a positive number and the negative terms add up to a negative number. So for example, it could be, 2, the positive terms, and minus 7, the negative terms. And then no matter how you reshuffle this series, the sum will always be 2 minus 7 is minus 5. Okay, now there's something else that we're actually doing here. We're actually bracketing, right? So we're bracketing. So we can bracket like this, or we can bracket like that, or maybe we don't do any brackets whatsoever. And actually, as long as we're dealing with infinite series that converge, either this type or of that type, doesn't matter what, you can put in brackets any way you want and the sum won't change. So I mean that's a bit reassuring. So basically commutativity is broken, but associativity, at least for convergent series, doesn't get mucked up. That's quite nice. But there's at least one more surprise happening here. That's just for convergent series. So if you actually look at some divergent series, strange things can happen even when you bracket them. So for example, this guy here, the 1 minus 1 plus 1 minus 1 divergence series, if you just bracket it right, you'll actually get a convergent series with a certain sum. And actually you can bracket this in many, many different ways and get different sums out. And maybe that's also a puzzle for you to sort out. How can you re-bracket this thing to get different sums out? Well, there's really amazing things to be discovered yet. The first one is basically saying, and you can actually, with what I showed you today, you can actually figure out the details yourself, is that if I give you an arbitrary infinite series, there's 3 different cases. So you can ask, in how many different sums can I rearrange this thing? So the first case is, no matter how I rearrange this thing, I'll never get a sum. Second case is, it rearranges in all possible sums. And the third case is, it just has one sum, no matter how you rearrange it. Now, this gets even freakier when you're considering infinite series of complex numbers or infinite series of vectors, and you can do this in Banach spaces and all kinds of other things. But maybe that's enough for today.
Hey Vsauce, Michael here. What is the biggest number you can think of? A Google? A Googleplex? A millinillion Olplex? Well, in reality, the biggest number is 40. Covering more than 12,000 square meters of Earth, this 40, made out of strategically planted trees in Russia, is larger than the battalion markers on Signal Hill in Calgary, the 6 found on the Fauvin badges in England, even the mile of pi Brady unrolled on Numberphile. 40 is the biggest number on Earth in terms of surface area. But in terms of amount of things, which is normally what we mean by a number being big, 40 probably isn't the biggest. For example, there's 41. And then there's 42, and 43, a billion, a trillion. You know, no matter how big of a number you can think of, you could always go higher. So there is no biggest last number. Except infinity? No. Infinity is not a number. Instead, it's a kind of number. You need infinite numbers to talk about and compare amounts that are unending. But some unending amounts, some infinities, are literally bigger than others. Let's visit some of them and count past them. First things first, when a number refers to how many things there are, it is called a cardinal number. For example, 4 bananas, 12 flags, 20 dots. 20 is the cardinality of this set of dots. Now, 2 sets have the same cardinality when they contain the same number of things. We can demonstrate this equality by pairing each member of one set 1-to-1 with each member of the other. Same cardinality, pretty simple. We use the natural numbers, that is 0, 1, 2, 3, 4, 5, and so on, as cardinals whenever we talk about how many things there are. But how many natural numbers are there? It can't be some number in the naturals because there'd always be 1 plus that number after it. Instead, there's a unique name for this amount: Aleph Null. Aleph is the first letter of the Hebrew alphabet, and Aleph Null is the first, smallest infinity. It's how many natural numbers there are. It's also how many even numbers there are, how many odd numbers there are. It's also how many rational numbers, that is, fractions, there are. That may sound surprising, since fractions appear more numerous on the number line, but as Cantor showed, there's a way to arrange every single possible rational such that the naturals can be put into a 1-to-1 correspondence with them. they have the same cardinality. Point is, Aleph Null is a big amount. Bigger than any finite amount. A Googleplex, a Googleplex factorial to the power of a Googleplex to a Googleplex squared times Graham's number? Aleph Null is bigger. But we can count past it. How? Well, let's use our old friend, the supertask. If we draw a bunch of lines and make each next line a fraction of the size and a fraction of the distance from each last line, well, we can fit an unending number of lines into a finite space. The number of lines here is equal to the number of natural numbers that there are. The two can be matched 1 to 1. There's always a next natural, but there's also always a next line. Both sets have the cardinality Aleph Null. But what happens when I do this? Now, how many lines are there? Aleph Null plus 1? No. Unending amounts aren't like finite amounts. There are still only Aleph Null lines here because I can match the naturals 1 to 1 just like before. I just start here and then continue from the beginning. Clearly, the amount of lines hasn't changed. I can even add 2 more lines, 3 more, 4 more. I always end up with only Aleph Null things. I can even add another infinite Aleph Null of lines and still not change the quantity. Every even number can pair with these and every odd number with these. There is still a line for every natural. Another cool way to see that these lines don't add to the total is to show that you can make this same sequence without drawing new lines at all. Just take every other line and move them all together to the end. It's the same thing. But hold on a second. This and this may have the same number of things in them, but clearly there's something different about them, right? I mean, if it's not how many things they're made of, what is it? Well, let's go back to having just one line after an Aleph Null sized collection. What if, instead of matching the naturals 1 to 1, we insist on numbering each line according to the order it was drawn in? So we have to start here and number left to right. Now, what number does this line get? In the realm of the infinite, labeling things in order is pretty different than counting them. You see, this line doesn't contribute to the total, but in order to label it according to the order it appeared in, well, we need a set of labels, of numbers, that extends past the naturals. We need ordinal numbers. The first trans-finite ordinal is omega, the lowercase Greek letter omega. This isn't a joke or a trick. It's literally just the next label you'll need after using up the infinite collection of every single counting number first. If you got omegath place in a race, that would mean that an infinite number of people finished the race, and then you did. After omega comes omega plus 1, which doesn't really look like a number, but it is, just like 2 or 12 or 800. Then comes omega plus 2, omega plus 3. Ordinal numbers label things in order. Ordinals aren't about how many things there are. Instead, they tell us how those things are arranged. They're order type. The order type of a set is just the first ordinal number not needed to label everything in the set in order. So, for finite numbers, cardinality and order type are the same. The order type of all the naturals is omega. The order type of this sequence is omega plus 1, and now it's omega plus 2. No matter how long an arrangement becomes, as long as it's well ordered, as long as every part of it contains a beginning element, the whole thing describes a new ordinal number. Always. This will be very important later on. It should be noted at this point that if you are ever playing a game of who can name the biggest number, and you're considering saying omega plus 1, you should be careful. Your opponents might require the number you name to be a cardinal that refers to an amount. These numbers refer to the same amount of stuff, just arranged differently. Omega plus 1 isn't bigger than omega, it just comes after omega. But Aleph Null isn't the end. Why? Well, because it can be shown that there are infinities bigger than Aleph Null, that literally contain more things. One of the best ways to do this is with Cantor's diagonal argument. In my episode on the Banach-Tarski paradox, I used it to show that the number of real numbers is larger than the number of natural numbers. But for the purposes of this video, let's focus on another thing bigger than Aleph Null, the power set of Aleph Null. The power set of a set is the set of all the different subsets you can make from it. For example, from the set of 1 and 2, I can make a set of nothing, or 1, or 2, or 1 and 2. The power set of 1, 2, 3 is the empty set, 1, and 2, and 3, and 1 and 2, and 1 and 3, and 2 and 3, and 1, 2, 3. As you can see, a power set contains many more members than the original set. 2 to the power of however many members the original set had, to be exact. So, what's the power set of all the naturals? Well, let's see. Imagine a list of every natural number. Cool. Now, the subset of all, say, even numbers would look like this. Yes, no, yes, no, yes, no, and so on. The subset of all odd numbers would look like this. Here's the subset of just 3, 7, and 12. And how about every number except 5? Or no number except 5? Obviously, this list of subsets is going to be, well, infinite. But imagine matching them all 1-to-1 with a natural. If, even then, there's a way to keep producing new subsets that are clearly not listed anywhere here, we will know that we've got a set with more members than there are natural numbers. A bigger infinity than Aleph Null. The way to do this is to start up here in the first subset and just do the opposite of what we see. 0 is a member of this one, so our new set will not contain 0. Next, move diagonally down to 1's membership in the second subset. 1 is a member of it, so it will not be in our new one. 2 is not in the third subset, so it will be in ours, and so on. As you can see, we are describing a subset that will be, by definition, different in at least one way from every single other subset on this Aleph Null-sized list. Even if we put this new subset back in, diagonalization can still be done. The power set of the naturals will always resist a 1-to-1 correspondence with the naturals. It's an infinity bigger than Aleph Null. Repeated applications of power set will produce sets that can't be put into 1-to-1 correspondence with the last. So it's a great way to quickly produce bigger and bigger infinities. The point is, there are more cardinals after Aleph Null. Let's try to reach them. Now remember that after omega, ordinals split, and these numbers are no longer cardinals. They don't refer to a greater amount than the last cardinal we reached, but maybe they can take us to one. Wait, what are we doing? Aleph Null? Omega? Come on, we've been using these numbers like there's no problem. But if at any point down here, you can always add 1. Always. Can we really talk about it, this endless process, as a totality and then follow it with something? Of course we can. This is math, not science. The things we assume to be true in math are called axioms. And an axiom we come up with isn't more likely to be true if it better explains or predicts what we observe. Instead, it's true because we say it is. Its consequences just become what we observe. We are not fitting our theories to some physical universe whose behavior and underlying laws would be the same whether we were here or not. We are creating this universe ourselves. If the axioms we declare to be true lead us to contradictions or paradoxes, we can go back and tweak them or just abandon them altogether, or we can just refuse to allow ourselves to do the things that cause the paradoxes. That's it. What's fascinating, though, is that in making sure the axioms we accept don't lead to problems, we've made math into something that is, as the saying goes, unreasonably effective in the natural sciences. So to what extent we're inventing all of this, or discovering it, it's hard to say. All we have to do to get omega is say, "Let there be omega," and it will be good. That's what Ernest Zermelo did in 1908 when he included the axiom of infinity in his list of axioms for doing stuff in math. The axiom of infinity is simply the declaration that one infinite set exists, the set of all natural numbers. If you refuse to accept it, that's fine. That makes you a finitist, one who believes only finite things exist. But if you accept it, as most mathematicians do, you can go pretty far, past these and through these. Eventually we get to omega plus omega, except we've reached another ceiling. Going all the way out to omega plus omega would be to create another infinite set. And the axiom of infinity only guarantees that this one exists. Are we going to have to add a new axiom every time we describe Aleph Null more numbers? No. The axiom of replacement can help us here. This assumption states that if you take a set, like say the set of all natural numbers, and replace each element with something else, like say bananas, what you're left with is also a set. That sounds simple, but it's incredibly useful. Try this. Take every ordinal up to omega, and then, instead of bananas, put omega plus in front of each. Now we've reached omega plus omega, or omega times 2. Using replacement, we can make jumps of any size we want, so long as we only use numbers we've already achieved. We can replace every ordinal up to omega with omega times it to reach omega times omega, omega squared. We're cooking now. The axiom of replacement allows us to construct new ordinals without end. Eventually, we get to omega to the omega to the omega to the omega to the omega, and we run out of standard mathematical notation. No problem. This is just called epsilon naught, and we continue from here. But now, think about all of these ordinals, all the different ways to arrange Aleph Null things. Well, these are well ordered, so they have an order type, some ordinal that comes after all of them. In this case, that ordinal is called omega 1. Now, because by definition, omega 1 comes after every single order type of Aleph Null things, it must describe an arrangement of literally more stuff than the last Aleph. I mean, if it didn't, it would be somewhere in here. But it's not. The cardinal number describing the amount of things used to make an arrangement with order type omega 1 is Aleph 1. It's not known where the power set of the naturals falls on this line. It can't be between these cardinals because, well, there aren't cardinals between them. It could be equal to Aleph 1. That belief is called the continuum hypothesis. But it could also be larger. We just don't know. The continuum hypothesis, by the way, is probably the greatest unanswered question in this entire subject. And today, in this video, I will not be solving it, but I will be going higher and higher to bigger and bigger infinities. Now, using the replacement axiom, we can take any ordinal we've already reached, like, say, omega, and jump from Aleph to Aleph all the way out to Aleph omega. Or heck, why not use a bigger ordinal like omega squared to construct Aleph omega squared? Aleph omega 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 omega. Our notation only allows me to add uncountably many omegas here, but replacement doesn't care about whether or not I have a way to write the numbers it reaches. Wherever I land will be a place of even bigger numbers, allowing me to make even bigger and more numerous jumps than before. The whole thing is a wildly accelerating feedback loop of embiggening. We can keep going like this, reaching bigger and bigger infinities from below. Replacement and repeated power sets, which may or may not line up with the Alephs, can keep our climb going forever. So clearly there's nothing beyond them, right? Not so fast. That's what we said about getting past the finite to omega. Why not accept as an axiom that there exists some next number so big no amount of replacement or power setting on anything smaller could ever get you there? Such a number is called an inaccessible cardinal because you can't reach it from below. Now, interestingly, within the numbers we've already reached, a shadow of such a number can be found. Aleph Null. You can't reach this number from below either. All numbers less than it are finite, and a finite number of finite numbers can't be added, multiplied, exponentiated, replaced with finite jumps a finite number of times, or even power set a finite number of times to give you anything but another finite amount. Sure, the power set of a millinillion to a googolplex to a googolplex to a googolplex is really big, but it's still just finite, not even close to Aleph Null, the first smallest infinity. For this reason, Aleph Null is often considered an inaccessible number. Some authors don't do this though, saying an inaccessible must also be uncountable, which, okay, makes sense. I mean, we've already accessed Aleph Null. But remember, the only way we could is by straight up declaring its existence axiomatically. We will have to do the same for inaccessible cardinals. It's really hard to get across just how unfathomable the size of an inaccessible cardinal is. I'll just leave it at this. The conceptual jump from nothing to the first infinity is like the jump from the first infinity to an inaccessible. Set theorists have described numbers bigger than inaccessibles, each one requiring a new large cardinal axiom asserting its existence, expanding the height of our universe of numbers. Will there ever come a point where we devise an axiom implying the existence of so many things that it implies contradictory things? Will we someday answer the continuum hypothesis? Maybe not, but there are promising directions. And until then, the amazing fact remains that many of these infinities, perhaps all of them, are so big, it's not exactly clear whether they even truly exist or could be shown to in the physical universe. If they do, if one day physics finds a use for them, that's great. But if not, that's great too. That would mean that we have, with this brain, a tiny thing a septillion times smaller than the tiny planet it lives on, discovered something true outside of the physical realm. Something that applies to the real world, but is also strong enough to go further, past what even the universe itself can contain or show us or be. And as always, thanks for watching.
Josephus problem. It's based on something from history. There was a group of Jewish soldiers who were surrounded by the Roman army, and they didn't want to get captured, so they decided to come up with a system to avoid getting captured or suicide. So they'd sit in a circle, and the first man would kill the guy to the left of him. The next remaining living person would kill the next remaining living person with their sword, and they'd go around like this until there's only one person left, and then the last person would have to commit suicide, of course, rather than get captured. And the story, at least the story I was told, I'm not sure this is historically accurate, was that Josephus preferred capture to suicide, but he worried that if he said this, the other soldiers would turn on it. And so he wanted to figure out where should he sit within this circle in order to be the last man living. And then he would surrender rather than kill himself. That was the problem. It's a little tricky, so let's do a smaller example. Let's say there were 7 people. And so just to be clear, the way it works is person number 1 kills number 2. Person number 3 kills 4. 5 kills 6. But now things get a little harder to kind of see in advance, because 7, there is no 8, so 7 kills 1. 3 kills 5. 7 kills 3. So 7's the winner. 7's the last one left over. For Josephus, there were 41 people. He needed to figure out where to sit. The mathematical problem is if there were n people, where's the winning seat? When I learned this problem, I was in high school. And it was one of the first problems that got me to understand how you approach difficult and math problems where you don't know the answer in advance, where someone hasn't shown it to you in advance. And it was a professor of mine. His name was Phil Hanlon, who played a big role in kind of leading me to math. And he suggested what we should do is we should gather data. Just take various values of n and just do it by hand and start looking for a pattern. I don't know, maybe we should just do that. N is the number of seats, and W of n will be the winning seat. And so what we know so far is that n is 7, W of n, it turns out, is also 7. And so what I would do is I'd start doing some other values. So I don't know, why don't I do 5? So 1 kills 2, 3 kills 4, 5 kills 1, 3 kills 5. The winner is 3. I guess there was no reason for me to skip 6, so why don't we fill in 6? Kills 2, 3 kills 4, 5 kills 6, kills 3, 5 kills 1. The winner is 5. So if you're watching, you might already start to notice some patterns. For instance, they're always odd. I mean, that's maybe the first thing you notice. And you can start to ask yourself, well, why are they always odd? And maybe you can already see that, right? The first loop around, all the even people get killed. So you can even with just a tiny amount of experiments start to see some patterns.
So you don't want to sit in an even seat.
Don't sit in an even seat. No. And maybe we're even getting some glimmers of other patterns. But before I really try to phrase those, I'd like to fill in the table a little bit more. So let's do some. So if there's only one person, well, that person's the winner. So that one was easy. If there's 2 people, 1 kills 2, 1's the winner. If there's 3 people, 1 kills 2, 3 kills 1, 3's the winner. If there's 4 people, 1 kills 2, 3 kills 4, 1 kills 3. If there's 8 people, 1 kills 2, 3 kills 4, 5 kills 6, 7 kills 8. 1 kills 3, 5 kills 7, 1 kills 5, winner is 1. All right, so it was 1, 1, 3, 1, 3, 5, 7, 1, 3, 5, 7, 9. And you could keep going, but maybe you can see the pattern now.
I think it's 13 or 1.
No, good guess, actually, but it's not a 1.
Brilliant.
So let's do 13.
This is good. I don't know then. I can't see the pattern.
So as you see, it's jumping by 2 each time, but then it resets at some point. And I want to go back to this. So we'll see what 13 is quickly.
Cool.
So we didn't reset there. I claim we won't reset at the next one either. 14 will be 13. And here, by the way, we're starting to make predictions. It's worth noting even though we maybe can't say exactly what like 178 would be, we're starting to see the pattern well enough that we could make a prediction. So you could guess, is it really true that 14 is going to give you 13? And we could do it out, and you'll see, in fact, that's what you'll get. So we're getting some understanding. But I want to go back to this point you had. You asked if it was going to reset and go back to 1 there. And the answer was no. And it's worth looking, because this is the next thing I was going to do. Where do we get the 1s? So if you look for a sec, there's something very special about the numbers that give you 1s. It's the powers of 2. And so maybe you can now guess that if I put in a 16, I would get a 1 back. And that'll be right. And that's actually going to be a real key in unlocking this. The professor I was learning this from made a really big point out of this. And I thought, well, I don't know what the general answer is yet. And he made a big point. If you know something, prove it and make sure you really understand that one thing. And that often unlocks the rest. So he really pushed us when I was first doing this to try to state a conjecture and then prove a theorem based on what we just saw here. And so that's what I want to do. So here's the conjecture, is that if n is a pure power of 2, then the winning seat is 1. I want to think about this for a second and maybe see why this might be true. So let's do the next biggest power of 2, maybe the biggest one I can bother writing down. So let's do 16. So I want to do one pass through the circle.
Take out all the evens.
Take out all the evens. And now 15 has just killed 16. So I'm going to put a little dot here so we remember it's number 1's turn again. And it's number 1's turn again, and we've removed all the evens, and what's left is therefore exactly half as many. So if I relabeled at this point, you can see that there was a power of 2 to start with. I pass through the circle once, I get rid of all the evens, I have half as many, and I'm back at number 1's turn. So now if I do this again, the same thing ought to happen, right? I should kill all the evens under the new labeling. And now there are 4 people left, and it's still number 1's turn. So you go through again, kill those guys. There's 2 people left. It's still number 1's turn. And now 1 kills that, and it's still number 1's turn, and that chair wins. So let's say we believe that. We know what happens for 2 to the n. So how do we explain what happens between the pure powers of 2? If you see the pattern, we know what happens at 8, and we know what happens at 4. But between them, it goes up by 2s until, at this point, if I added 2 to 7, I'd have a 9, which would be too big anyway. So that's our reset. But we knew it was going to reset because it's a pure power of 2. So how do we explain this jumping by 2 phenomena in between? And so what I'm going to do, I'm going to just mention that for any number, you can write it as a big power of 2 plus something else. Take the biggest power of 2 you can subtract from a number, and then what's left should be smaller than that. When you express a number in binary notation, you choose zeros or ones, and that gives it as a sum of a bunch of powers of 2, and you just choose the biggest one. So 77, the biggest power of 2 I can get is 64, and then what is it? It's 64 plus 13. So then for 13, the biggest power of 2 is 8 plus 4 plus 1. Did I do this right? 72, 77, there you go. And these are all powers of 2. And this is unique. This is the unique way to write 77 as a sum of powers of 2, where no power is repeated. That's a key point. So if you wanted to take a general number, take the biggest power of 2, 64, and then the remaining part, 12, 13. I'm going to call this part 2 to the a, and the remaining part I'm going to call L. And I claim that this L is going to tell us which of those odd numbers between is going to show up. So let's see how. How about we do 13? N is 13. This is the binary expansion, but using our new method, the 8 will be the 2 to the a, and the 5, which is the 4 plus 1, that'll be the L. And here's the thing that's going to happen with the L. I'm going to do 5 steps. So 1 kills 2, 3 kills 4, 5 kills 6, 7 kills 8, 9 kills 10. So now I've dropped L people, and it's number 11's turn. Now watch what happens. How many people are left? Well, what's left is a power of 2. And we know who wins in a power of 2. It's whoever starts.
The first killer.
The first killer. So now, if we go from here, I claim that 11's going to win. And just watch. It's going to be 11 kills 12, 13 kills 1, 3 kills 5, 7 kills 9. Back to 11, and now there's only 4 people left. 11 kills 13. 3 kills 7, back to 11, 2 people. 11 wins. And so this is really the key to the final answer, which is if you've written your number as 2 to the a plus L, after L steps, whosever turn it is going to win, because it's going to be their turn and there'll be a power of 2 left. And so the winning seat will be 2L plus 1 if you write it in this way, because that's whose turn it'll be after L steps. The theorem, or the claim, is that if you've written n in this way, so if n is 2 to the a plus L, where L is less than 2 to the a, it has to be strictly smaller. So in other words, 2 to the a is the biggest power that sat inside of n. Then the winning seat is going to be 2L plus 1. So we've already seen it was true here, right? L was 5, and the winning seat was 11, which is 2 times 5 plus 1. And if you start going back through, you'll see the same thing for all the answers. We've already really illustrated the mechanism, which is after L steps, it's the turn of person 2L plus 1. And after L steps, there are a power of 2 number of people left. And And when there's a power of 2 people, the first person who kills, that's who's going to be the winner.
Let's see if Brady has learned.
Yeah, all right, let's do
try
it.
this. I think I followed. Now, in the Josephus problem,
Yep,
there was Josephus and 40 soldiers. So,
that's right. Oh yeah, we got to go back and do that.
All right, so we've got 41 people.
So n is 41.
All right. So now, I think expressing that in the way you told me to, it's going to be 32 plus 9.
There you go, 32 plus 9.
So 2 lots of 9 plus 1 is 19.
There we go.
So we want to sit in position 19.
There you go. You want to sit in the 19th chair. So here we go. We're going to do n equals 41.
All right. Put them in the cave, waiting their fate.
Not a very good circle,
That's
but
right. Small them down.
I know. Should I redo this?
No, you're okay.
40, 41. Okay, there we are. So we got a little tight at the end.
Look
All
at
right.
that. This is a lesson about planning ahead, people.
Yeah. Okay, so let's do it. 1 kills 2, 4, 5.
We're losing our even numbers.
Yep. Okay, now 41 kills 1. 3 kills 5. And 19 kills 35, and there we go.
All right. I was right.
There we go, 19.
Right.
I'll note one other thing in this problem, which is kind of fun. So this formula I wrote can be interpreted in binary notation. When we wrote a number as a sum of powers of 2, this can be re-expressed in binary notation. So what was this? 32 plus 8 plus 1. So that's 2 to the 5th plus 2 cubed plus 2 to the 0. And binary notation, the digits correspond to the various powers of 2, and all the digits are 0 or 1. So 41 in binary notation would be 1 copy of 2 to the 5th, 0 of 2 to the 4th, 1 of 2 to the 3rd, 0, 2 squared, 0, 2 to the 1st, 1 to the... Here's a trick for the Josephus problem, which I won't justify, but it's super cool, and you can try it on your own. The way to find the winning solution, if this is n, the winning solution in binary is you take the leading digit and you put it at the end. So in other words, I claim that if I write 0, 1, so I take this part and then I add the first digit to the end, that number in binary code is, well, let's see, it's 2 to the 0 plus 2 to the 1 plus, I skipped 2 squared and I skipped 2 cubed, and I add 2 to the 4th. So it's 2 to the 4th plus 2 to the 1 plus 2 to the 0, which is 16 plus 2 plus 1, which is 19, which is exactly what the winning seat was. And so there's this super efficient way in binary code to jump straight from the number n to the winning number w of n. So if you're writing your numbers in binary code, the pattern would have been even more quickly apparent. Isn't that cool?
Yeah.
Yeah.
Hi everybody, Jade here. Today's video is about one of the most famous paradoxes in mathematical history. It's called Russell's paradox, named after Bertrand Russell, super cool dude, very influential philosopher slash mathematician slash logician slash social activist slash Nobel Prize winner. So yeah, we'll get to know all about him. But this is probably one of my favorite paradoxes, and it's really one of those ones that just makes you really question everything, question everything you know. So yeah, I'm super excited for this video. Just before we get into it, I just want to say that this is probably the most nuanced video I've ever done. There's a lot of subtleties and there's a lot of philosophy. So if you find that you're getting a bit lost or you need to rewind or watch the video again, that's totally normal, and I'd actually be pretty surprised if you got everything the first time. So yeah, let's get right into it. So first I'm going to introduce you to a somewhat simpler version of the paradox, just to soften some of the concepts that we're going to talk about later on. So this one is called the barber paradox, and it goes like this. There is a town with one barber, and his task is to shave all and only those who do not shave themselves. Now the question is, does the barber shave himself? Think about it. If the barber does not shave himself, then he should. And if he does shave himself, then he shouldn't. So So keep this little riddle at the back of your mind throughout the rest of the video. But now let's get right into the math. So Russell's paradox is ultimately about the foundation of mathematics. But some of you might be unfamiliar with that concept. What is a foundation of mathematics? Well, let's draw an analogy with the other sciences. The sciences are kind of like a tree. Biology is the study of living organisms, which are the result of millions and millions of chemical interactions. So one could conclude that all branches of biology stem from chemistry, or that chemistry is in some way foundational to biology. Likewise, chemical reactions are ultimately physical interactions, so one could conclude that all branches of chemistry stem from physics. If we keep going down in this way, we'll eventually come to the elementary particles that make up our universe, electrons and quarks. The laws that govern these particles can be considered the foundations of science, in that the rest of the sciences stem from them. If we were to discover something completely new about them, it would somewhat affect our understanding of the other sciences, even if only at the theoretical level. In the 19th century, each branch of math was pretty disconnected from the other branches, and there was no unifying trunk. Mathematicians at the time wanted to unify the branches of mathematics, and therefore a foundational theory was needed. But what made it tricky is that the approach to figure out the foundations of math is very different to that of the other sciences. We learn about the other sciences by observing the outside world, whether it be watching cells under a microscope, measuring orbits through a telescope, or smashing particles together at insanely high speeds. But we can't really learn more about mathematics by observing the outside world. Math seems to be something that just is. We can imagine a universe where the fundamental building blocks are different, or where time goes backwards, or where everything was made of antimatter. But we can't really imagine a universe where 2 + 2 = 5. Math is different in that it seems to be true by definition, and even though it's very good at describing our universe, it doesn't seem to be about our universe. Why? That is the question at the heart of this paradox. Now it's here that we steer away from the harder sciences and head more toward the study of what reality really is. Philosophy. We come to the first character in our story. The question, why is math the way it is, captured one of the greatest philosophical minds of all time, Plato. Plato thought that mathematical objects, numbers, shapes, and the relationships between them were objective truths. That is, objects that existed independently of us and our world. He thought they existed in their own world, which he called the world of forms. But one of Plato's pupils, Aristotle, had his own views. Unlike Plato, he thought that numbers themselves weren't objects, but properties of objects. For example, if there were 4 cows in a field, it wasn't that cows were an object and 4 was also an object, but the number 4 was a property of the collection of cows. He also thought they didn't exist in their own world of forms independent of our world, but they described features of our world and so belonged to our world. Another colourful philosopher, Immanuel Kant, soon came along, and he didn't like the view that mathematical objects were objective truths, and believed that to understand the basic principles of math, you needed some kind of intuition. That yes, math described our world, but we also brought it to the world from our experience. Now this is where our quiet hero of the story comes along, Gottlob Frege. Yes, interestingly, Bertrand Russell is not the main player in Russell's paradox, but a German mathematician named Frege. The story of Frege is somewhat tragic as he was largely ignored during his life and 20 years of his life's work was unjustly washed down the drain, but here he will be remembered as a god among us. Frege disagreed with Aristotle's view that numbers were properties of objects because of this argument. If numbers are properties of object, then only one number should belong to any object, and it shouldn't be influenced by matter of opinion. But then, imagine a pair of shoes. Is it one pair of shoes, or is it 2 shoes? Depending on how we conceptualize an object, the number belonging to it changes. Again, imagine a deck of cards. Depending on how we conceptualize it, it could be 1 deck of cards or 52 cards. So Frege concluded that numbers don't apply to objects, but to concepts. He also disagreed with Kant that to understand math you needed intuition and experience, stating that the laws of arithmetic can be known from the basis of reason alone. I sought to make it plausible that arithmetic is a branch of logic and need not borrow any ground of proof whatever from either experience or intuition. Frege's main goal was to reduce mathematics to logic and show that logic is in fact the foundation of math. This idea is known as logicism. Now, the notion of logic that Frege had in mind is pretty similar to how we would use it in everyday language. But just to make it super clear, logic is a tool for reasoning about how different statements affect each other through nothing more than deduction and inference. For example, if we take it as a fact that all dogs have a good sense of smell, and Tiffa is a dog, deductive reasoning will tell you that Tiffa has a good sense of smell. I don't know if this is the best example though, because she's pretty old. I don't know if she can smell much anymore. But you get the idea. Frege started his quest of reducing math to logic by coming up with a definition of what number was. Now, this might seem like a somewhat trivial question to some of you, what is a number? But remember, at the heart of Frege's paradox was the idea that you don't need any kind of intuition or experience to understand mathematics. And when you think about it, have you ever actually tried to describe what a number is without using the word number or words derived from the word number? I've spent some time trying as I was writing this video, and I found that I always ended up using the word number again, or a word that was directly related to number, like amount or quantity. Give it a go right now and let me know what you come up with in the comments. Frege defined numbers by using this idea of concepts and extensions. A concept is pretty much any idea you can think of. The color red, sheep, Bill and Bob, Shakespeare's plays, hipsters, elephants with no ears, literally any idea. And an extension is the set of all things that fall under that concept. For the concept the color red, its extension would be the set of all red things, past, present, and future. The concept Bill and Bob would be made of the extension of the Bill and Bob you were referring to. If we have a concept like square circles, which doesn't make sense, their extension would simply be the empty set, a set with nothing in it. Numbers, Frege stated, are extensions of concepts. For example, the number 4 is the extension of the concept of all things made up of a collection of this many objects. The number 7 is the extension of the concept of all things made up of a collection of this many objects. Frege built his foundation of mathematics from the axiom that all concepts we can possibly think of have a corresponding extension, and therefore there are as many extensions as there are concepts. He named this the general comprehension principle, and it sounds reasonable, right? Can you think of a concept that doesn't have a corresponding set to go with it? I don't think I could. But Bertrand Russell did. Frege was just about to have his work printed when he received a letter from Bertrand Russell in June 1901, which read along the lines of, "Dear colleague, I find myself in complete agreement with you in all essentials. In regard to many particular questions, I find in your work discussion, distinctions, and definitions that one seeks in vain in the works of other logicians. There is just one point where I have encountered a difficulty. Consider the set of all sets that are not members of themselves. Is that set a member of itself?" This simple question shattered Frege's foundation and caused him a mental breakdown so severe he ended up in hospital, and later caused him to write, "My efforts to throw light on the question surrounding the word number seems to have ended in complete failure." Let's break it down. First, a word about sets. Sets are a collection of things. You can even have sets within sets. Take, for example, the set of all sets of bird species. There exists the set of all penguins, the set of all seagulls, the set of all pigeons, and the set of all other bird species, and they themselves would make up the set of all sets of bird species. Most sets are not members of themselves. That is, they don't fall under themselves. For example, the set of all teapots is not a teapot. The set of all turtles is not a turtle. But what about the set of all things that are not turtles? Because it's a set and not a turtle, it is a member of the set of all things that are not turtles. Therefore, the set of all things that are not turtles is a member of itself. A lot of sets are members of themselves, and there's nothing too extraordinary about that. But the question that Russell asked was, is the set of all sets that are not members of themselves a member of itself? Think about it. If it is a member of itself, then it is not. And if it's not a member of itself, it is. Sound familiar? I'll say it again. If it is a member of itself, then it's not. And if it's not a member of itself, it is. Now, the reason that this was so catastrophic is because the last thing you want in a neat, systematized, axiomatized description of anything is a contradiction. Imagine if one of the foundational laws of physics predicted that gravity both always pulls and always pushes. It'd be a pretty useless law. When your system is able to derive two opposite theorems, this puts into question the entire theory. Numerous attempts were made to correct this hiccup, like Russell's theory of types, which tried to put sets into some kind of hierarchy. But many thought that this fix was too artificial and ad hoc. Frege eventually felt forced to abandon many of his views about logic and math. Even so, as Russell points out, Frege met the news of the paradox with remarkable fortitude. As I think about acts of integrity and grace, I realize that there is nothing in my knowledge to compare with Frege's dedication to truth. His entire life's work was on the verge of completion. Much of his work had been ignored to the benefit of men infinitely less capable. His second volume was about to be published, and upon finding that his fundamental assumption was an error, he responded with intellectual pleasure, clearly submerging any feelings of personal disappointment. It was almost superhuman and a telling indication of that of which men are capable, if their dedication is to creative work and knowledge instead of cruder efforts to dominate and be known. Apparently he didn't know about the breakdown. Anyway, after a series of fortunate events, the foundations of mathematics is now known to be a system called Zermelo-Fraenkel set theory, which has a lot of Frege's original ideas incorporated into it. But, although this is currently the most widely accepted theory, the search still isn't over, with candidates like category theory and homotopy type theory becoming serious contenders for that much desired position at the bottom of the math tree. But that is for another video.
This is Zeno of Elea, an ancient Greek philosopher famous for inventing a number of paradoxes, arguments that seem logical but whose conclusion is absurd or contradictory. For more than 2,000 years, Zeno's mind-bending riddles have inspired mathematicians and philosophers to better understand the nature of infinity. One of the best known of Zeno's problems is called the dichotomy paradox, which means the paradox of cutting in two in ancient Greek. It goes something like this. After a long day of sitting around thinking, Zeno decides to walk from his house to the park. The fresh air clears his mind and helps him think better. In order to get to the park, he first has to get halfway to the park. This portion of his journey takes some finite amount of time. Once he gets to the halfway point, he needs to walk half the remaining distance. Again, this takes a finite amount of time. Once he gets there, he still needs to walk half the distance that's left, which takes another finite amount of time. This happens again and again and again. You can see that we can keep going like this forever, dividing whatever distance is left into smaller and smaller pieces, each of which takes some finite time to traverse. So, how long does it take Zeno to get to the park? Well, to find out, we need to add the times of each of the pieces of the journey. The problem is, there are infinitely many of these finite-sized pieces. So, shouldn't the total time be infinity? This argument, by the way, is completely general. It says that travelling from any location to any other location should take an infinite amount of time. In other words, it says that all motion is impossible. This conclusion is clearly absurd, but where's the flaw in the logic? To resolve the paradox, it helps to turn the story into a math problem. Let's suppose that Zeno's house is 1 mile from the park, and that Zeno walks at 1 mile per hour. Common sense tells us that the time for the journey should be 1 hour. But let's look at things from Zeno's point of view and divide up the journey into pieces. The first half of the journey takes half an hour. The next part takes 1/4 of an hour. The third part takes 1/8 of an hour, and so on. Summing up all these times, we get a series that looks like this. Now, Zeno might say, since there are infinitely many terms on the right-hand side of the equation, and each individual term is finite, the sum should equal infinity, right? This is the problem with Zeno's argument. As mathematicians have since realized, it is possible to add up infinitely many finite-sized terms and still get a finite answer. How, you ask? Well, Let's think of it this way. Let's start with a square that has area 1 unit. Now let's chop the square in half, and then chop the remaining half in half, and so on. While we're doing this, let's keep track of the areas of the pieces. The first slice makes 2 parts, each with an area of 1/2. The next slice divides one of those halves in half, and so on. But no matter how many times we slice up the boxes, the total area is still the sum of the areas of all the pieces. Now you can see why we chose this particular way of cutting up the square. We've obtained the same infinite series as we had for the time of Zeno's journey. As we construct more and more blue pieces, to use the math jargon, as we take the limit as n tends to infinity, the entire square becomes covered with blue. But the area of the square is just 1 unit, and so the infinite sum must equal 1. Going back to Zeno's journey, we can now see how the paradox is resolved. Not only does the infinite series sum to a finite answer, but that finite answer is the same one that common sense tells us is true. Zeno's journey takes 1 hour.
Did humans just make up mathematics? As in, are prime numbers just a figment of our collective imagination? Or do they really exist, separate from our human minds? To start, here's a fairly simple math statement. The Goldbach conjecture says that every even number is the sum of 2 primes. A prime number is one that's only divisible by itself and 1, like 2, 3, 5, 7, 11, 13, 17, and so on. For example, 6 is not prime because it's divisible by 2 and 3. So the Goldbach conjecture says that every even number is a prime number plus another prime. For example, 4 is 2 plus 2, 8 is 3 plus 5, 20 is 7 plus 13, and so on. Prime numbers are defined by, and principally about, multiplication and division. But the Goldbach conjecture is about what happens when you add them. That's part of what's weird about the Goldbach conjecture, and mathematics in general. Humans pick how to define mathematical objects, but then those objects take on a life of their own and have properties and behaviors we didn't intend. This throws into question whether or not math exists independently of the human mind. In the case of the Goldbach conjecture, we picked the definition of prime number, and then their relationship with even numbers just sort of sprung up. In this way, mathematics can feel like you wrote the first page of a book, and then you're figuring out the rest. Nobody had to write the next page, it just sort of unfolds, like you're tapping into a story that was already written, which is strange. And what gets even stranger about the Goldbach conjecture is that in the nearly 300 years since the conjecture was formulated, nobody has ever proved it. Computers have tested even numbers up to this huge number, and they've always been able to find 2 primes that add up to the even number. But mathematicians don't have a proof that it holds for all even numbers. And this points to something really important about math. Math isn't like science, where you gain enough evidence and declare something true. You have to have a precise logical proof. In this sense, mathematics is about perfect knowledge. Individual mathematicians may make logical mistakes, but whole mathematical theories aren't disproven the way they are in science. Mathematical knowledge just accumulates rather than revises itself. But what is all this knowledge about? Well, it's about mathematical objects like prime numbers. And numbers are weird objects. In fact, there's a serious debate about whether numbers even exist. You can't see or touch them, which makes them seem sort of made up. But unlike most fictions, numbers never change. You can make up new rules for checkers, but 2 plus 3 is always gonna be 5. And besides, if numbers don't really exist, how come we can use them to construct skyscrapers that don't fall over? Let's move away from prime numbers and try to answer these questions with another mathematical object, the circle. In school, you probably learned that pi is the ratio of the circumference to the diameter of a circle. This statement is not about a real circle. Real circles have defects, and while the number pi is infinitely precise, any real measurement has a limited amount of precision. So actually, pi is the ratio of the circumference to the diameter of a perfect circle. This fact about the definition of pi seems simple enough, but there are actually 2 very different ways to interpret it. The first option is called realism. A realist would say that there is some fixed, idealized circle, and all mathematicians throughout all of space and time are talking about the properties of that circle. Pi is the ratio of the circumference to the diameter of that circle. Realists think that the objects that mathematicians study are real, really real, and exist independently of the humans that think about them. So a perfect circle exists, just like a water molecule or the planet Jupiter exist. One version of this is called Platonism, as in the ancient Greek philosopher Plato and his idea of Platonic forms. There's a form of a circle, and all circular things in the physical world embody that form. But mathematicians aren't studying physical circles. They're studying the Platonic form of a circle, just as chemists study molecules and astrophysicists study planets. Here's what's great about realism. It aligns with the way people feel while doing math. It positions mathematicians as investigators of sorts. They're like explorers in a sea of numbers and shapes and ideas. It's how actual mathematicians talk. But Platonism leads to a big problem. Where does our knowledge of these forms come from? Actual explorers learn by physical interactions. When Neil Armstrong famously described the surface of the moon, he was relying on his senses like touch and sight. Photons were bouncing off the moon into his eyeballs. But when Goldbach saw the connection between even numbers and primes, it's hard to believe he was literally interacting with the Platonic forms of the numbers. If numbers, or a perfect circle, exist, how do we access them to learn about them? This question is irritating enough that many philosophers of math have taken the opposite approach, anti-realism. Let's go back to our fact about pi. Pi is the ratio of the circumference to the diameter of a circle. The anti-realist would say that mathematicians just made up the rules for being a circle and are drawing out the consequences of those rules. One version of this is called formalism, which sort of equates mathematics with a game, like chess. Mathematicians are playing out the rules of the game. It's dependent on the human minds that created it. What's great about formalism is that it solves the problem of Platonism. We know things about math because we made up the rules. We don't have to look anywhere else. The problem in treating math like it's completely made up is what mathematician Eugene Wigner described as the unreasonable effectiveness of mathematics in the natural sciences. Math is robust and an amazingly precise language to describe everything from quantum mechanics to the stock market. It's hard to imagine that a game so accurately describes reality. Knowing the rules of chess doesn't help scientists launch rockets into space, but knowing math does. That's part of why it's so difficult to understand what math is. Mathematician Reuben Hirsch wrote that the working mathematician is a Platonist on weekdays, a formalist on weekends. At the end of the day, most mathematicians, this one included, are content just mathing it. Mathematicians love their subject. It's beautiful and mysterious, abstract yet concretely descriptive, whatever it is. Which camp do you fall into?
There's a famous way to seemingly create chocolate out of nothing. Maybe you've seen it before. This chocolate bar is 4 squares by 8 squares. But if you cut it like this, and then like this, and finally like this, you can rearrange the pieces like so and wind up with the same 4 by 8 bar, but with a leftover piece apparently created out of thin air. There's a popular animation of this illusion as well. I call it an illusion because it's just that, fake. In reality, the final bar is a bit smaller. It contains this much less chocolate. Each square along the cut is shorter than it was in the original, but the cut makes it difficult to notice right away. The animation is extra misleading because it tries to cover up its deception. The lost height of each square is surreptitiously added in, while the piece moves to make it hard to notice. I mean, come on. Obviously, you cannot cut up a chocolate bar and rearrange the pieces into more than you started with. Or can you? One of the strangest theorems in modern mathematics is the Banach-Tarski paradox. It proves that there is in fact a way to take an object and separate it into 5 different pieces. And then, with those 5 pieces, simply rearrange them, no stretching required, into 2 exact copies of the original item. Same density, same size, same everything. Seriously, to dive into the mind blow that it is and the way it fundamentally questions math and ourselves, we have to start by asking a few questions. First, what is infinity? A number? I mean, it's nowhere on the number line, but we often say things like, there's an infinite number of blah blah blah. And as far as we know, infinity could be real. The universe may be infinite in size and flat, extending out forever and ever without end, beyond even the part we can't observe or ever hope to observe. That's exactly what infinity is. Not a number per se, but rather a size. The size of something that doesn't end. Infinity is not the biggest number. Instead, it is how many numbers there are. But there are different sizes of infinity. The smallest type of infinity is countable infinity, the number of hours in forever. It's also the number of whole numbers that there are. Natural numbers, the numbers we use when counting things like 1, 2, 3, 4, 5, 6, and so on. Sets like these are unending, but they are countable. Countable means that you can count them from one element to any other in a finite amount of time. Even if that finite amount of time is longer than you will live, or the universe will exist for, it's still finite. Uncountable infinity, on the other hand, is literally bigger. Too big to even count. The number of real numbers that there are, not just whole numbers, but all numbers, is uncountably infinite. You literally cannot count even from 0 to 1 in a finite amount of time by naming every real number in between. I mean, where do you even start? 0, okay, but what comes next? 0.000000. Eventually, we would imagine a 1 going somewhere at the end, but there is no end. We could always add another 0. Uncountability makes this set so much larger than the set of all whole numbers that even between 0 and 1, there are more numbers than there are whole numbers on the entire endless number line. Gero-Cantor's famous diagonal argument helps illustrate this. Imagine listing every number between 0 and 1. Since they are uncountable and can't be listed in order, let's imagine randomly generating them forever with no repeats. Each number we generate can be paired with a whole number. If there's a 1-to-1 correspondence between the two, that is, if we can match one whole number to each real number on our list, that would mean that countable and uncountable sets are the same size. But we can't do that. Even though this list goes on forever, forever isn't enough. Watch this. If we go diagonally down our endless list of real numbers and take the first decimal of the first number and the second of the second number, the third of the third, and so on, and add 1 to each, subtracting 1 if it happens to be a 9, we can generate a new real number that is obviously between 0 and 1, but since we've defined it to be different from every number on our endless list in at least one place, it's clearly not contained in the list. In other words, we've used up every single whole number, the entire infinity of them, and yet we can still come up with more real numbers. Here's something else that is true but counterintuitive. There are the same number of even numbers as there are even and odd numbers. At first, that sounds ridiculous. Clearly, there are only half as many even numbers as all whole numbers, but that intuition is wrong. The set of all whole numbers is denser, but every even number can be matched with a whole number. You will never run out of members of either set, so this one-to-one correspondence shows that both sets are the same size. In other words, infinity divided by 2 is still infinity. Infinity plus 1 is also infinity. A good illustration of this is Hilbert's paradox of the Grand Hotel. Imagine a hotel with a countably infinite number of rooms. But now, imagine that there is a person booked into every single room. Seemingly, it's fully booked, right? No. Infinite sets go against common sense. You see, if a new guest shows up and wants a room, all the hotel has to do is move the guest in room number 1 to room number 2, and the guest in room 2 to room 3, and 3 to 4, and 4 to 5, and so on. Because the number of rooms is never ending, we cannot run out of rooms. Infinity minus 1 is also infinity again. If one guest leaves the hotel, we can shift every guest the other way. Guest 2 goes to room 1, 3 to 2, 4 to 3, and so on. Because we have an infinite amount of guests, that is a never-ending supply of them, no room will be left empty. As it turns out, you can subtract any finite number from infinity and still be left with infinity. It doesn't care. It's unending. Banach-Tarski hasn't left our sights yet. All of this is related. We are now ready to move on to shapes. Hilbert's hotel can be applied to a circle. Points around the circumference can be thought of as guests. If we remove one point from the circle, that point is gone, right? Infinity tells us it doesn't matter. The circumference of a circle is irrational. It's the radius times 2 pi. So if we mark off points beginning from the hole, every radius length along the circumference going clockwise, we will never land on the same point twice. Ever. We can count off each point we mark with a whole number. So this set is never ending, but countable, just like guests in rooms in Hilbert's hotel. And like those guests, even though one has checked out, we can just shift the rest, move them counterclockwise, and every room will be filled. Point 1 moves to fill in the hole, point 2 fills in the place where point 1 used to be, 3 fills in 2, and so on. Since we have an unending supply of numbered points, no hole will be left unfilled. The missing point is forgotten. We apparently never needed it to be complete. There's one last neato consequence of infinity we should discuss before tackling Banach-Tarski. Ian Stewart famously proposed a brilliant dictionary, one that he called the Hyperwebster. The Hyperwebster lists every single possible word of any length formed from the 26 letters in the English alphabet. It begins with A, followed by AA, then AAA, then AAAA, and after an infinite number of those, AB, then ABA, then ABAA, ABAAA, and so on until Z, ZA, ZAA, etc., until the final entry, an infinite sequence of Z's. Such a dictionary would contain every single word, nay, every single thought, definition, description, truth, lie, name, story. What happened to Amelia Earhart would be in that dictionary, as well as every single thing that didn't happen to Amelia Earhart. Everything that could be said using our alphabet. Obviously, it would be huge, but the company publishing it might realize that they could take a shortcut. If they put all the words that begin with A in a volume titled A, they wouldn't have to print the initial A. Readers would know to just add the A because it's the A volume. By removing the initial A, the publisher is left with every A word sans the first A, which has surprisingly become every possible word. Just one of the 26 volumes has been decomposed into the entire thing. It is now that we're ready to investigate this video's titular paradox. What if we turned an object, a 3D thing, into a Hyperwebster? Could we decompose pieces of it into the whole thing? Yes. The first thing we need to do is give every single point on the surface of the sphere one name and one name only. A good way to do this is to name them after how they can be reached by a given starting point. If we move this starting point across the surface of the sphere in steps that are just the right length, no matter how many times or in what direction we rotate, so long as we never backtrack, it will never wind up in the same place twice. We only need to rotate in 4 directions to achieve this paradox: up, down, left, and right, around 2 perpendicular axes. We are going to need every single possible sequence that can be made of any finite length out of just these 4 rotations. That means we will need left, right, up, and down, as well as left, 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 up, left, down, but of course not left, right, because, well, that's backtracking. Going left and then right means you're the same as you were before you did anything. So no left rights, no right lefts, and no up downs, and no down ups. Also, notice that I'm writing the rotations in order right to left, so the final rotation is the leftmost letter. That will be important later on. Anyway, a list of all possible sequences of allowed rotations that are finite in length is, well, huge. Countably infinite, in fact. But if we apply each one of them to a starting point, in green here, and then name the point we land on after the sequence that brought us there, we can name a countably infinite set of points on the surface. Let's look at how, say, these 4 strings on our list would work. Right, up, left. Okay, rotating the starting point this way takes us here. Let's color code the point based on the final rotation in its string. In this case, it's left, and for that we will use purple. Next up, down, down. That sequence takes us here. We name the point DD and color it blue since we ended with a down rotation. RDR, that will be this point's name, takes us here, and for a final right rotation, let's use red. Finally, for a sequence that ends with up, let's color code the point orange. Now, if we imagine completing this process for every single sequence, we will have a countably infinite number of points named and color coded. That's great, but not enough. There are an uncountably infinite number of points on a sphere's surface. But no worries, we can just pick a point we missed, any point, and color it green, making it a new starting point, and then run every sequence from here. After doing this to an uncountably infinite number of starting points, we will have indeed named and colored every single point on the surface just once. With the exception of poles. Every sequence has 2 poles of rotation, locations on the sphere that come back to exactly where they started. For any sequence of right or left rotations, the poles are the north and south poles. The problem with poles like these is that more than one sequence can lead us to them. They can be named more than once, and be colored in more than one color. For example, if you follow some other sequence to the north or south pole, any subsequent rights or lefts will be equally valid names. In order to deal with this, we're going to just count them out of the normal scheme and color them all yellow. Every sequence has 2, so there are a countably infinite amount of them. Now, with every point on the sphere given just one name and just one of 6 colors, we are ready to take the entire sphere apart. Every point on the surface corresponds to a unique line of points below it all the way to the center point, and we will be dragging every point's line along with it. The lone center point we will set aside. Okay, first we cut out and extract all the yellow poles, the green starting points, the orange up points, the blue down points, and the red and purple left and right points. That's the entire sphere. With just these pieces, you could build the whole thing. But take a look at the left piece. It is defined by being a piece composed of every point accessed via a sequence ending with a left rotation. If we rotate this piece right, that's the same as adding an R to every point's name. But left and then right is a backtrack, they cancel each other out. And look what happens when we reduce them away. The set becomes the same as a set of all points with names that end with L, but also U, D, and every point reached with no rotation. That's the full set of starting points. We have turned less than a quarter of the sphere into nearly 3/4 just by rotating it. We added nothing. It's like the hyperwebster. If we add the right piece and the poles of rotation and the center point, well, we've got the entire sphere again, but with stuff left over. To make a second copy, let's rotate the up piece down. The down-ups cancel because, well, it's the same as going nowhere, and we're left with a set of all starting points, the entire up piece, the right piece, and the left piece. But there's a problem here. We don't need this extra set of starting points. We still haven't used the original ones. No worries, let's just start over. We can just move everything from the up piece that turns into a starting point when rotated down. That means every point whose final rotation is up. Let's put them in the down piece. Of course, after rotating, points named UU will just turn into points named U, and that would give us a copy here and here. So as it turns out, we need to move all points with any name that is just a string of U's. We will put them in the down piece and rotate the up piece down, which makes it congruent to the up, right, and left pieces. Add in the down piece along with some up and the starting point piece, and, well, we're almost done. The poles of rotation and center are missing from this copy, but no worries. There's a countably infinite number of holes where the poles of rotation used to be, which means there is some pole around which we can rotate this sphere such that every pole hole orbits around without hitting another. Well, this is just a bunch of circles with one point missing. We fill them each like we did earlier, and we do the same for the center point. Imagine a circle that contains it inside the sphere and just fill in from infinity. And look what we've done. We have taken one sphere and turned it into two identical spheres without adding anything. 1 + 1 = 1. That took a while to go through, but the implications are huge, and mathematicians, scientists, and philosophers are still debating them. Could such a process happen in the real world? I mean, it can happen mathematically, and math allows us to abstractly predict and describe a lot of things in the real world with amazing accuracy. But does the Banach-Tarski paradox take it too far? Is it a place where math and physics separate? We still don't know. History is full of examples of mathematical concepts developed in the abstract that we did not think would ever apply to the real world for years, decades, centuries, until eventually science caught up and realized they were totally applicable and useful. The Banach-Tarski paradox could actually happen in our real world. The only catch, of course, is that the 5 pieces you cut your object into aren't simple shapes. They must be infinitely complex and detailed. That's not possible to do in the real world, where measurements can only get so small and there's only a finite amount of time to do anything. But math says it's theoretically valid, and some scientists think it may be physically valid too. There have been a number of papers published suggesting a link between Banach-Tarski and the way tiny subatomic particles can collide at high energies and turn into more particles than we began with. We are finite creatures. Our lives are small and can only scientifically consider a small part of reality. What's common for us is just a sliver of what's available. We can only see so much of the electromagnetic spectrum. We can only delve so deep into extensions of space. Common sense applies to that which we can access, but common sense is just that, common. If total sense is what we want, we should be prepared to accept that we shouldn't call infinity weird or strange. The results we've arrived at by accepting it are valid. true within the system we use to understand, measure, predict, and order the universe, perhaps the system still needs perfecting. But at the end of the day, history continues to show us that the universe isn't strange. We are. And as always, thanks for watching.
Não consigo mais acompanhar.